Hello everyone and welcome to today's webinar, which is the fourth in the series on how oil industry skills are helping new energy technologies. I'm Matthew Laskay and I will be your host for today's session as we're talking about geothermal energy. How will it support the drive to net zero and what opportunities will it create for individuals within the oil and gas sector? In this series so far, we've covered a wide range of topics such as hydrogen, carbon capture and storage, and next month we'll be talking about wind energy. So if you missed any of those, please have a look at the IMechE webinar hub for the recordings and remember to register for the one on the 28th of Feb. As always, we'll be taking your questions at the end of today's webinar, so please keep sending them through in the Q&A section on the screen throughout the session and we will do our best to answer them. But today it's all about geothermal. And I'm pleased to introduce today's main presenter. Running his own consultancy after 3 decades in upstream oil and gas, John Clegg is now blogging on the topics of innovation and the energy transition and has just completed his second book on innovation. John's also the CTO of Hydrothermal Energy Technology, which is a company founded to repurpose technology created for the oil and gas industry in order to develop an ultra-high temperature drilling system for the geothermal industry, and also to enable a new generation of deep, hot, closed-loop geothermal wells. So to give you a bit more information, welcome John, take it away.
Good morning everybody, and I'm going to spend some time now talking to you about geothermal energy and how it can play a role in our energy transition. I'm going to talk to you about what geothermal energy is and how our perception of it has developed over the years and why we should be interested in it now as a scalable source of clean energy for the planet, and how that picture might have changed recently and how the role of geothermal might change over the next few years compared with what it has been over the last centuries and even millennia, as I'll show you in a minute. I'm going to talk about some of the key similarities with and differences to well construction for oil and gas wells, because I'm kind of coming at this from the perspective of transition for oil and gas skills and technologies into a new industry. Those similarities and differences present us with opportunities, and those opportunities can be seen as opportunities for people and for organizations in oil and gas to move into geothermal, to pivot, and also can be seen as opportunities for adjacent high technology industries who might be able to bring some of the technologies and techniques that could be required to scale geothermal for us. But it's always good to start with a bit of history. We've been using geothermal for about 10,000 years, and here's an example from not too far from where I'm sitting today in Bath Spa in the UK. That's about 2,000 years old, the Roman baths. This illustrates that heat isn't necessarily just found in those traditional geothermal locations that I'm going to talk about in a minute. It could be found underneath some of our most historic and picturesque towns and cities, as you can see. But the first use of geothermal power to generate electricity, which is what I'm really going to be focusing on today, dates from 1904, less than 120 years ago, in a place called Laderillo in Italy. I'm going to focus today on the hotter and deeper wells that are more likely to be used for power generation than for heating, because that's where I think the bigger opportunity for geothermal energy lies. Now, I started to migrate from oil and gas towards geothermal a couple of years ago, 2 or 3 years ago. And I was very skeptical at first because I used to think about geothermal energy being associated with tectonic activity and hot rocks close to the surface in places like Iceland, New Zealand, Indonesia, maybe parts of the Mediterranean and Turkey, where there is there's volcanic heat which is close to the surface. This particular picture is the Iceland volcano that erupted last year, 2021. And to my surprise and to my pleasure, it turns out that there is geothermal energy available in other places as well. This is a geothermal power station in Iceland. This uses steam from hot water reservoirs to drive turbines to generate electricity, and this works very much like a coal-fired or nuclear-fired power station would. You create steam, you use that steam to generate electricity from turbines. And so far, as a population, we have seen geothermal energy and electricity being generated from hydrothermal wells. So what does hydrothermal mean? Well, it turns out that there's actually potentially quite a broad spread of applications for geothermal. Direct use is things like ground heat pumps that can be used for residential applications, heat your house in the winter and cool it in the summer. It can be used quite extensively for agriculture, for keeping greenhouses warm, for example. And that's just taking the heat from under the ground and bringing it to the surface and using it without conversion. Hydrothermal wells are drilled to exploit reservoirs of hot water underground. From the hot water you get steam, and that steam drives a turbine to generate electricity. In some parts of the world, hydrothermal is a significant part of the energy mix. For example, in California, which is close to tectonic activity, it provided about 6% of the electricity demands in 2020. But demand for electricity is growing faster than the capabilities of hydrothermal. And there are a couple of other systems that I'm going to talk about a little bit today. These are enhanced and advanced geothermal systems. And basically what these systems do is create artificial reservoirs. So you don't actually need to have a reservoir of hot water down there. You create a network of either pipework or fractures in the rock, and you actually get heat from the rock. So instead of drilling for hot water, with EGS and AGS you're drilling for heat, and I'll explain how that works in a minute. But once you start to think about drilling for heat, you're no longer restricted to those locations I was talking about. There's heat underneath our feet anywhere in the world. It's just a question of how deep you go. And the hope is, and the expectation is, that EGS and AGS will allow us to drill deep underneath our feet, any country in the world, and exploit the heat that's down there, either coming from the center of the Earth or being generated within radioactive formations down there. This illustration just gives you a kind of pictorial indication of what I was just talking about. On the left, you can see ground source heat pumps and the like, which we may well use in future to power a lot of, to provide a lot of the heat and cooling for our houses. And then as you move across to the right, you're getting into hydrothermal and then enhanced geothermal systems to provide heat and electrical power. And technical complexity and power generation kind of increase from left to right, as do depth and as does temperature of the formation. So I'm going to come back and talk a bit more about EGS and AGS in a few minutes and explain what they are. But before I do that, I just wanted to talk a bit more about why geothermal is potentially so important to us. This looks at greenhouse gas emissions, and it looks at various sources of energy in terms of life cycle greenhouse gas emissions. And you can see non-renewable stuff is on the right, natural gas, oil and coal, the last three on the right, as you would expect, have got the largest emissions. Geothermal, you can see in the center of the left-hand block of renewable resources, and you can see GHG emissions from geothermal energy is very low. There's a certain amount of emissions which is going to be locked into producing a facility, drilling a well and building a power station. But overall, it's low, and it's very competitive with wind and with solar. But the big advantage that geothermal has got is capacity, and capacity is basically how much time it can be generating for. And a lot of the criticisms you hear of wind and solar is, Well, you don't get wind energy when the wind doesn't blow, and you don't get solar electricity at night. And unless you augment them with battery storage or some other kind of thermal storage, that is going to be the case. Geothermal has the capability to operate close to 100% of the time and produce heat, sort of day and night, regardless of the weather. And that puts it above any other of the renewable energy sources in that respect. So it has this unique combination of low GHGs and high capacity. But what about the cost? Well, the cost isn't as bad as you might think it is. This is analysis that was done a couple of years ago by Lazard, and you can see various types of energy represented. It's a very busy slide. Geothermal is represented as being between about $59 and $101 per megawatt hour of electricity, which is certainly competitive with or lower than coal, cheaper than nuclear, and it overlaps with the upper level of natural gas. So it's not as cheap as other sources of energy at the moment, including wind or gas, but it's not too far away. And it's heading in the right direction. We talked to a number of the what I'm going to call the unconventional geothermal companies. These are geothermal companies that are looking to exploit this EGS and AGS technology, and they're talking about getting to about $50, which is below the lower end of that scale I just showed you, and kind of within the cost environment inhabited by things like natural gas and wind and solar. Rystad Energy in Norway is projecting rapid growth over the next decade in the number of geothermal wells drilled for power generation. Unfortunately, they're projecting rapid growth from a fairly modest level. So they're projecting growth from around 100 to 200 wells per year, which we've seen over the last few decades, to maybe 700 to 800 wells a year by 2030. That is, I believe, a relatively unambitious, low-end estimate of what could happen. Just to give you a slightly less modest estimate, the exponential growth comes after 2030, but the scale on this particular one is massive. This is not really a prediction. This is kind of a thought experiment that was produced by a company called British company Causeway GT last year. And they're looking about, what could the future look like? And you can see here they're talking about over 2.5 million geothermal wells per year by 2040. I think this includes low enthalpy wells, things heating and cooling and ground source and so on. But it does illustrate how geothermal could continue to grow to 2040 and beyond. And it won't surprise you that my own company's estimates of where the market is likely to be is bigger than the Rystad numbers and smaller than these numbers here. One thing that we do think will happen is that the costs of geothermal will decline as scale comes on. And these are numbers showing how wind and solar costs have declined over the last decade as technology has become available, as people have invested, and as scale has grown. And they follow, to anybody who studies the cost of products and technologies, they follow a fairly predictable asymptotic decline down to a long-term level. And we don't believe that geothermal has got there yet. That kind of reduction in cost with scale and with experience is very similar to what was seen in the oil and gas industry in unconventional oil and gas wells in the US in the last decade or two. Everybody thought that George Mitchell was crazy when he started to experiment with the extraction of gas from the Barnett Shale, but using a combination of horizontal drilling and hydraulic fracturing, he was able to get gas from places where people didn't believe it could be economically extracted. And those two technologies, horizontal drilling and hydraulic fracturing, completely changed the game for oil and gas in North America. So the question is, what do those two technologies, horizontal drilling and hydraulic fracturing, have to do with geothermal energy? And the answer is potentially quite a lot. And now I'm going to explain to you what these enhanced and advanced geothermal systems actually are. There are many different flavors of these systems, so I'm showing you some schematics that give you an idea of how they work. There are lots of different ideas with lots of different companies for lots of different ways of implementing them. As is often the case when you see a new technology emerge, there are often very many different forms of that technology. And it's only after a few years or possibly even a few decades that we see a dominant form emerge and dominate the market. But in principle, enhanced geothermal systems, or EGS, will drill two wells, an injector and a producer, and will create an artificial fracture between them, or may exploit a natural fracture and possibly enhance it with an artificial fracture. So the fracture in the rock gives you a path whereby you can inject into the blue well fluid, which could be water or it could be something like carbon dioxide, will flow from the injector to the producer through the rock, getting heated up as it goes, and then will return up the producer as hot fluid that will convert to steam and then allow you to generate power in your power station. This requires fracturing, and it may also require directional or possibly even horizontal drilling. Here are a few different styles of advanced geothermal systems, and what advanced geothermal systems tend to do is to produce a loop downhole without doing the hydraulic fracturing. So the one in the center is a U-shaped well, where one side of that is going to be the injector, the other is the producer. The one on the left is a fairly complex looking downhole radiator, which is the concept of Ever, a company based in Canada. And the one on the right is a single well, which is coaxial. So you will pump cold fluid down and get hot fluid back, and have some kind of insulation between in a piece of pipe between the hot and the cold fluid. And it's possible to combine both directional and coaxial systems with fracturing and produce some kind of a hybrid system. So you have what's effectively a closed loop system, but you also use fracturing to expose the surface area with which the fluid is exposed to the rock, and allow better heat transfer from the rock, and to get fluid back to the surface. But what all of these systems do is they will pump down cold fluid, get hot fluid back without taking any fluid from the formation. They don't look for reservoirs of fluid, they provide all their own fluid, and we're just mining the heat. And if you look at some of the directional wells that have been drilled, look at the horizontal well in this one, for example, you can ask yourself, don't they just look like oil and gas wells? And yeah, they do. They will use directional and horizontal drilling, and in some cases they may also use hydraulic fracturing. So they're wells that us in the oil and gas industry know how to drill. And you listen to a guy called Vic Rao, who was Chief Technology Officer of Halliburton in Houston, Texas, is now Executive Director of this energy consortium, does a lot of blogging, has his own video blog, and in one of his recent blogs he said, oil and gas service companies who've positioned themselves as leaders in high temperature and high pressure drilling, the kind of drilling that's going to be required for geothermal, are going to own this future. Basically, he's saying there's a very bright future for people who develop the technology required to drill these wells. And that's the theme I'm going to return to later on. So they look a bit like oil and gas wells. But what are the key differences? And I'll talk to you about the key differences are things that make it difficult for us, but they're also things that open up potential opportunities for us. So the first one, and the most obvious one, is temperature and pressure. There are a few different definitions of what high pressure, high temperature wells are. This one here is from Schlumberger, where they're talking about anything over 150 degrees Celsius, 10,000 psi is high pressure, high temperature. API has a different definition, which is 177 Celsius and 15,000 psi. There are probably other definitions that you can find as well. The point is that geothermal tends to be deeper and hotter than what oil and gas would consider to be high temperature and high pressure. So geothermal is right out in the top right hand corner, and certainly on the upper part of the chart that you see on the screen here. I thought it would be useful to compile a list of all the commercial oil and gas measurement and drilling tools that are capable of operating at the moment, or rated for operating above 200 degrees Celsius. And this is the list. There's nothing which is currently capable of operation above those temperatures according to their manufacturers. There is one minor exception to that I'll talk about later, and I'll return to talk about temperature later. But there are some other challenges and opportunities associated with geothermal that I thought would be useful to look at in the meantime. So this is a picture of one of the tours on Dartmoor, and this was the site of many years ago, longer than I care to remember. This was the site of a school trip for me, and I remember standing on top of one of the tours with my geography teacher, and he asked me if I noticed anything about the other tours, and I said no, and he said, well, they're all the same height, and within sort of reasonable tolerance, many of the tours on Dartmoor are approximately the same height. And the way he explained it to me is that there were these granite intrusions in the earth, lots of sedimentary formation had filled in between them, and the whole lot was scraped off clean by the ice age. And so basically everything was scraped to the same height. And then over the intervening years, many years since the ice age, the other formations have been washed away to form the slopes and the hills like the one you see in the background, and the granite intrusions still remain, because granite is tough stuff. Basically, it's a lot tougher than the other formations we try to drill. And when you're trying to drill sort of granite and basement rocks, the kind of rocks we're going to be drilling to get these geothermal installations done, there are some particular challenges. One of those challenges is friction. There's a very high coefficient of friction with igneous rocks compared with drilling sedimentary rocks. That means that wellbore quality, the straightness of the well, is more important, and continuous rotation of the drill string to overcome axial sliding friction is also important. And we'll come back to both of those later on. If you're drilling highly fractured formations with drilling fluids, you could well see significant amount of losses. And in order to counter those mud losses, sometimes people will use air or foam drilling, or sometimes you'll see pressurized mud cap drilling to minimize the cost of the fluid. You basically have a sacrificial fluid that you put into all the fractures in the formation. And these kind of techniques that have been pioneered by the oil and gas industry are likely to be very applicable to drilling the fractured formations we're going to see drilling geothermal wells. There's a lot of nasty stuff present in hot geothermal fluids, particularly if we're finding hydrothermal reservoirs that have got water in them, but also if we're introducing drilling fluid into some of the formations we're going to be drilling. You're going to see calcium and sodium ions. You're going to see CO2, H2S, hydrochloric acid, ammonia, all potentially present. And when you combine those with high temperature, you get some particular materials challenges. And as you see from the image here, which is a piece of drill pipe that's failed in sour service, you get challenges that you don't necessarily see in everyday oil and gas wells, and some opportunities for some advanced materials technologies, possibly from oil and gas, possibly imported from other industries. there has been a lot of effort to develop some fairly unusual and esoteric drilling technology for drilling these hard formations. The picture on the left is one of the finalists at a kind of Dragon's Den event that was done last year at a big geothermal event, Pivot 2021. Who are using, as you can see, ballistics to try and create holes in granite. There are people looking at things like lasers and particle-assisted drilling. But on the right-hand side, this is a well that was recently drilled in Utah in the US using regular rotary PDC drill bits as used in the oil and gas industry. They managed to drill the well about almost twice the speed that was planned, and were able to do so by leveraging existing oil and gas drill bits and existing technology. So it indicates that maybe there's more of a place for existing technology than we might think. Drilling fluids. For environmental reasons, we'd rather use water-based drilling muds, but they can lose viscosity at high temperatures and lose their ability to transport cuttings. So higher temperatures, oil-based muds are often preferred. They're less environmentally friendly, and also they have lower heat capacity. And it's very important, as you'll see in the next couple of slides, to be able to use the drilling fluid to take heat away from the equipment you're using to drill a well. Water-based muds would be better for that if they could maintain viscosity, and therefore there is the opportunity for people to develop higher temperature water-based drilling muds. Mud flow, as I just said, can be used to cool downhole tools. So with higher flow rates to provide more cooling, we're likely to see larger pumps and bigger drilling rigs, and also things like mud chillers to get the mud as cold as you can before you pump it down the hole. That's all going to help a little bit in taking a little bit more heat out of the equipment that's down there and trying to drill a well. Now, in oil and gas drilling, it's conventional to drill approximately 100 feet and then make a connection. You don't normally flow when you make the connection. And so if you're relying on the flow of drilling mud to cool stuff down, every time you make a connection, all the tools you've got downhole are going to get hot. And so it may well be that drilling geothermal wells is going to require continuous circulation systems that allow you to circulate fluid from the rig through the drilling assembly and through the hole, even while you're making a connection. These technologies exist, they're already on the market, they may become more popular in geothermal, and so that's got implications for rig selection and for rig design. But coming back to temperature, I mentioned earlier this Canadian company. These are basically 3 evolutions of their plans for downhole geothermal systems, and they're getting deeper and they're getting hotter. And so temperature is going to be a key requirement for us as we try and develop equipment for drilling these wells. Now, there is one LWD tool, logging while drilling tool, that's rated to 200 degrees Celsius. It was developed by a company called Weatherford in the US. It's been used in the North Sea, and it's also been used fairly extensively in the Gulf of Thailand, where there are some very high bottom hole temperatures. It's actually been used once, and I saw this in a customer presentation, so I'm not giving anything secret away, but it was, I think it was 213 or 216 Celsius because there were some circulation issues, and the tool survived at that temperature. So you can take downhole electronics above 200 Celsius, but this tool required a ground-up redesign. There was nothing in this tool that would look familiar to you if you looked at a standard downhole drilling tool that had been developed for about 175 Celsius operation. It couldn't be done with conventional electronics, and it couldn't be done with conventional electronics because plastic package components, they're just not going to survive at 200 Celsius. You could try and push them closer and closer to that temperature by selecting components and testing, but you get into diminishing returns, and to get above 200C, you really need a completely different approach. Possibly the approach that was pioneered by Weatherford in their HEX tool in the previous slide, possibly something slightly different. Now, luckily, we've got friends in other industries who are also trying to attack higher temperatures. This is an artist's impression of what the surface of Venus might look like, and NASA has plans to take a rover and land it on the surface of Venus in the not too distant future. It's going to be probably going to be a rover on the surface with power generation from the Venusian atmosphere, and it's going to have electronics in it, and those electronics are going to have to operate at about 480 Celsius, much hotter than we're talking about. So there are people who are interested in developing technologies that we could potentially leverage in the future, and there are also are people who I think have been working in aerospace and looking at temperatures in the 200 to 225 Celsius range, which is a near-term sweet spot potentially for downhole electronics and downhole components for drilling geothermal wells. So we may well be able to take sort of help from other industries, and that's going to require different packaging, different joining techniques, different ways of thinking about how we construct the electronics. But these ways of doing it, they're kind of known. We're not going to be completely reinventing the wheel. With apologies to NASA, it's not going to be rocket science. We do have technologies that we can take and that we can repurpose and that we can use to build downhole electronics for drilling these geothermal wells. This is from my own company. We have a vision of creating an integrated directional drilling tool for geothermal wells that will be autonomous, self-powered, have all the sensors and electronics it needs, and will be able to drill the kinds of profiles that we looked at in the earlier slides, and to be able to do so at temperatures initially of 225 Celsius and ultimately significantly beyond that. And we believe we can do that because we don't believe there's anything out there that we need that doesn't exist somewhere, that isn't perhaps already been done for our industry or by another industry. And that will enable us to drill wells that look a bit like this, where you can drill vertical wells that turn through to horizontal. You can drill wells that join, so you can make what's effectively a U-shaped well, and you can drill the fairly complex looking profiles that we saw in some of the earlier slides about AGS. And also, once we've developed a tool like this, we'll have the building blocks for high temperature electronics and sensing that allows us to do a number of other things as well. In addition to directional drilling and measurements, we'll be able to do logging of formation properties. We'll be able to build intelligent completions, and we'll be able to do things like production monitoring and production optimization of these geothermal wells. Even things as simple as measuring the downhole temperature, so we understand the impact we're having on the reservoir, and we understand if one of the dangers with geothermal is we try and take more heat from the reservoir than can be replenished through the thermal conductivity of the rock. If that's the case, we're going to need monitoring and optimization so that we can manage the reservoirs to make sure that we get the optimum level of production of electricity from them in the long run. But I believe there's an opportunity there. New technology transformed and scaled unconventional oil and gas over the last decade or two. And if we take new technology and our oil and gas expertise and decades of experience in the geothermal industry of drilling hydrothermal wells, if we could find ways of combining all that together, I believe that we can scale geothermal to previously unimagined heights, and we can provide a significant amount of the world's requirements for electricity, which, by the way, is probably going to double over the next 30 years without continuing to burn more and more greenhouse gas producing fuels, fossil fuels. And from an engineering and from a business point of view, this is our time. I just read Larry Fink's letter to CEOs. Larry Fink runs BlackRock, one of the big investment companies. And he says in his 2022 letter, I believe the decarbonizing of the global economy is going to create the greatest investment opportunity of our lifetime. He says specifically in his letter that being green and decarbonizing is not woke. It's actually really, really good business, and it provides great investment opportunities. And he goes on to predict that the next 1,000 unicorns, they're not going to be search engines or social media companies like maybe we've seen over the last decade or two. The new unicorns are going to be sustainable, scalable innovators, startups that help the world to decarbonize and make the energy transition affordable. And so if we are engineers thinking about providing technology that's going to drive the energy transition, now is our time. So what could I do? I mean, if I was working in oil and gas, or maybe working in an adjacent industry, if I had technology like high temperature electronics or advanced materials technology or ways of joining materials that I thought could be useful to this endeavor, one useful thing would be to follow some of the companies that are currently pioneering. There's a whole bunch of companies that are looking at either drilling hydrothermal wells or drilling what are called unconventional geothermal wells. There's a bunch of them listed on the slide here. The ones on the right in slightly larger images are UK-based companies who you can follow and who you can investigate. There are also trade bodies like these, Geothermal Rising, GEO at the University of Texas, the Society of Petroleum Engineers. These guys are all looking to a greater or lesser degree at geothermal and how important it is to our future. And I suggest that within IMechE we should be doing that as well. But as IMechE members, I think it's potentially useful for us to look at what these other organizations are doing and be informed by it and to learn from it. So whether your skills are from oil and gas or from industries like aerospace, think about how they could be applied. If you're an individual, think about how your skills, your experience and your training could be applied to geothermal. If you're a supplier, think about how your products and services and technologies could be applied to meet the needs that I just talked about, because I think there are opportunities in all of those needs, all of those areas where geothermal wells are going to be difficult to drill. They provide opportunities for all of us. So thanks for listening to me talk about geothermal. This is one of a series of talks. We've already heard about CCUS and hydrogen in earlier talks in this series. We're going to talk about wind energy on the 28th of February, and then on the 4th of April, we're going to come together and reprise all of these talks, explore potential next steps and explore latest developments. So look out for further announcements with a bit more detail about these events. And with that, I'd like to thank you for your attention. I've enjoyed talking for the last 35-40 minutes. I hope you've enjoyed listening, and I'm now happy to take any questions. Thank you.
Fantastic. Thank you very much, John. Some really interesting stuff there. I think it's pretty clear to see from the slides early on that there's not going to be one single solution for the next energy transition. And also, it's also going to be very closely aligned with oil and gas, both the skills and the technologies, but there's going to be some individual challenges that are unique to geothermal. So are you ready for some questions?
I am, yeah.
Excellent. So please keep those questions coming in if you haven't done it so already. So the first one, John, is you can maybe decide whether you agree with the statement or not with the way this is worded. Does it worry you at all that geothermal energy is a non-renewable source of energy?
That's a good question, and I'm actually glad you raised that one first, because I might throw it back a little bit at the questioner if they're still on the call, and give the opportunity to come back and explain exactly what they meant by that. But yeah, there is probably no source of energy which is completely renewable. Solar energy will expire when the sun goes out, and tidal energy actually takes energy from the system by which the moon orbits the Earth and so on. For all intents and purposes, geothermal energy is classified as renewable by people like the US Energy Information Administration because there is effectively, as far as humankind is concerned, effectively infinite supply of heat from the center of the Earth, which is it's being generated by radioactive decay of elements. So yeah, one day those elements will be expired and radioactive decay will stop. But I think I'm correct in saying that the sun's life is probably shorter than the life of that heat generation in the center of the Earth. So for all intents and purposes, I think it is renewable. Now, there are some challenges, and a couple of other questions I've seen come in get into the challenges of keeping it coming through rock because of thermal conductivity of rock. But we can get to those questions in a minute, and I can talk in a bit more detail about that when we get to those points. But if the question comes back with a clarification or ask in a different way, then we've got some time, so feel free.
Yeah, no problem. I'll keep an eye on that. So that was from a different John, if John's still listening.
Yeah.
So the next one then is around cost. So it's a slightly different spin, but the cost of geothermal is so cost competitive. If the cost of geothermal is so cost competitive and has a high availability, to some governments, such as the UK, seem to favour nuclear over it. There must be other factors that are going against it, like scalability or geography.
Yeah, I think there are a few, and I think the questioner there has hit the nail on the head with some of the issues. Geography is definitely one. I mean, we do have successful geothermal generation of electricity now in the UK, in Cornwall. And one of the reasons why it's in Cornwall is because the thermal gradient there is probably the highest in the UK, or one of the highest in the UK. And typically geothermal has been confined to what we call hydrothermal power generation, which is actually drilling for hot water and producing steam from naturally available water. And that has geographic limits. There are only a certain number of places in the world you can do that. I mean, I mentioned Cornwall. When you look around the world at traditional hydrothermal sites, you'll look at places like California, Turkey, Italy, Indonesia, Iceland. And one of the things that will strike you about all of those places is they're all places with fairly high levels of tectonic activity. Now, the unconventional geothermal I talked about allows us to get away from that geographic dependence, but then we're getting into scalability and cost, because the technologies I was talking about are technologies which are still in the process of being developed. So they don't necessarily exist yet, and I think the opportunity for our industry here is to participate in the development of those and the scaling of them to make them sufficiently cost effective. And the other thing, and I think, you know, if something good comes out of this presentation today, maybe one of them will be awareness, is geothermal always seems to be a little bit of a kind of Cinderella when it comes to looking at energy sources, and particularly renewable sources. And a lot of governments, not just the UK government, don't really seem to be aware of the potential. There is very little talk from the government in the UK about geothermal as a potential source of power, either as heat or electric power. And I think it's something that we should be taking a bit more seriously. And I think, you know, the danger is it's always been quite a small industry because of geographic limitations. And the danger is that it remains small just because it's small. And I think it has a lot more potential than that.
Right, okay, that's fair enough. And while we're on that same topic of government and maybe opposition and that, fracking is something that we saw come up particularly a couple of years ago. And with some of the concerns and opposition for some parts of the world that are against fracking, do you think this is going to be a barrier for exploiting the geothermal energy?
It's going to be a challenge, but there are different ways of getting heat from hot, dry rocks. The enhanced geothermal systems that I described certainly require fracking. Although it's generally at a lower pressure than the fracking which is used in unconventional oil and gas wells, and which has been controversial based on some reports of some experiences in the US.
Right.
Now, having said that, there have been some reports of induced seismicity, that's basically minor earthquakes caused by fracking of geothermal wells. I think there's at least one in Switzerland where there was a fracking of an enhanced geothermal well caused some minor seismic activity. But if you look at advanced geothermal systems, the closed loop systems, they don't require fracking. They will basically produce a downhole radiator, which will just get heat from the rock by virtue of the surface area contact between the formation and the fluids. There is a lot of opposition in Europe to fracking and stimulation. There is a part of me that wonders how high the price of natural gas will need to go before it begins to override that opposition. But we're probably getting into territory which is outside the scope of this discussion. But there are ways of getting geothermal energy from high temperature rocks which don't require fracking or stimulation. And it may be that in certain parts of the world those become more popular simply because they avoid kind of finesse that potential sort of public perception and opposition.
Okay. Well, I'll direct it back to, we'll get to some more technical questions now for you then. So a few of the specifics on the wells and things. So one of them is, when drilling the injector and producer wells, are they made in pairs?
It very much depends. There are lots of different designs of enhanced and advanced geothermal wells. At the outset of any new technology, you get lots of different competing potential solutions. And it's only over the course of a number of years that you see which of those solutions becomes dominant and eventually is the de facto standard for the industry. And that could take maybe decades instead of years. So if you look at the various options we looked at, some of them are actually single wells where the injection and the production happens in a coaxial piece of pipe in the same well. So you pump the fluid down the well and you get it back. You pump it down the bore and get it back up the annulus, or possibly vice versa. There are others where it's been shown schematically where you have like a U-shaped well, or maybe a U-shaped well with a radiator, downhole radiator in there. Most people show them as being in pairs, but I'm not sure it's necessarily the case that they need to be. You could imagine that solutions would emerge where they didn't have to be in pairs, and where you could inject fluid into one well in a system, and you could produce heat from another well, or maybe for another leg or another lateral in that same well.
Okay. There's a couple of questions, I suppose, while you're talking about temperatures and things, but so there's two people asking a similar question. Will the borehole lose its heat over time? How long does it take to recover? What's the bore life? And the other one was about heat yield. So maybe just if you expand a little bit on the heat exchange. I guess there's a few questions coming in on that.
Yeah, those are really good questions, because the borehole can potentially lose its heat over time. And this could be a significant challenge for the industry, and it's a technical challenge that people designing and constructing these wells is going to have to overcome. And the reason why it's a challenge is because the thermal conductivity of rock is very poor. It's just as well it is, or we'd all be burning our feet when we walked on the ground because of the heat present in the center of the earth. But from the perspective of producing heat from rock, it causes a problem, because if you imagine drilling a well through the rock to extract heat, you pull the heat away from the formation very quickly, and then because of the poor thermal conductivity of rock, it takes a while for effectively the heat to replenish and for you to be able to produce some more. This is not a problem that conventional hydrothermal wells have, because they actually use water as the medium for getting heat from the rock, and they go through natural fractures. So they're pulling from a much larger surface area. If you use an enhanced geothermal system where you've put artificial fractures into the rock, then you might have enough surface area over a large enough sort of piece of ground, large enough coverage to be able to match the rate at which you pull heat out with the rate at which the rock will conduct it back in. For advanced geothermal systems, you're producing from a single wellbore, and the ability of the rock to replenish heat into that wellbore is constrained because you imagine it's trying to do so through a set of concentric shells of rock, which get smaller and smaller as you get closer to the wellbore. And that acts a bit like a kind of a choke to limit the flow of heat from the formation into the well. So it gets difficult for the rock to heat the well back up as you get close. I have seen some studies of how quickly it will replenish. The stuff I've seen is confidential to the people who showed it to me, so I can't disclose it on the call here. But you could, if I talk about it a different way, you could imagine there might be a solution where you have a small number of wells or a small number of laterals off a mother well, and you just produce from them one at a time. So you imagine you've got a multilateral well where you've got one of the horizontal legs pointing north, one east, one south, and one west. Maybe you'd produce from the north for a short period of time, and then you'd switch and then produce from the eastern leg and then the southern leg and so on. And that kind of setup should allow enough time for the temperature and the non-producing legs to get sufficiently hot that they can give you the power you need when you get back to producing from them. So yeah, if you take a lot of heat out of the rock quickly, it can take a little bit of time to replenish. And it's not down to supply. There's an infinite, effectively, as far as we're concerned, an infinite supply of heat underground. It's just because of the ability of the rock to get it through.
Okay, I guess just you may have sort of partially answered this one, but so in the same way that GSHP can freeze the ground around the evaporator coil, do geothermal wells cool the rock to the point that it becomes unusable?
I don't think it will become unusable. It's just you have to allow it time to recover, or you have to be aware of the overall sort of heat transfer system, and be aware that the thermal conductivity of the rock getting the heat to the well is poor, and so that either constrains the rate at which you can take heat out, or it means that you have to switch between different legs and allow the non-producing legs to kind of recover. Hey Matthew, are you still there? I'm not hearing you.
Yep, sorry, I was just trying to move my slides there for a second.
Oh, no worries. Okay, I thought we had a connection issue for a minute.
No, I'm just trying to prevent the clicking mouse from making a noise while you're talking, while I'm trying to manage the questions. Simon says that a single well system is effectively a very long contraflow heat exchanger. If you inject cold fluid, you would not get hot fluid back. It would be hotter, but not by much. What's the temperature difference for it to be economical?
Yeah, that's one of the big challenges with the single well systems, the coaxial systems, is that they are exactly that. They could potentially become a very long heat exchanger. And so if you put your money in one of those systems, one of the challenges you have is insulating effectively the returns from the fluid that you put into the well. It's not the only challenge, because you're also bringing that hot fluid back through the formation, which is gradually getting colder. And in most locations, you'll also be pulling it through groundwater reservoirs when you get close to the surface. And that the water in the groundwater reservoirs is going to be very hungry for the heat. So you're going to have to think very carefully about insulation of the well from the formation as you get close to the surface. I think binary plants, I'm not an expert on power plants, okay, so I I'll very quickly get myself into trouble if I start to talk about power cycles and how plants work. My understanding is that flash cycles require fluid about 200 Celsius up. Binary plants can actually operate from about 100 degrees Celsius up. And so the economics depend on a whole bunch of things. It depends on the cost of drilling the well, which might be comparable to the cost of drilling like an unconventional oil and gas well. It's going to depend on the value of the power and the location, but one of the good things about geothermal is that you can actually produce electric power in the location where you need it, very close to the point of use. And so the economics are improved by not having to either install or maintain high tension transmission networks and stuff like that. The other big challenge for economics while we're talking about that is payback, because there's a potential for geothermal wells to generate power for a significant amount of time, like many decades. But when people are investing in infrastructure, like power stations, they're tending to look for much shorter returns. I mean, oil and gas has a huge advantage here because the returns are so quick. You drill a well and you're instantly making money. We did a bit of a thought experiment within the company where we looked at the amount of energy that you get from a typical unconventional oil or gas well in the US, a horizontal well, which is then fracked. And if you drilled a similar cost geothermal well, based on power estimates that we've got from some publicly available sources, we estimated that you would get the same amount of energy back from the well in about 16 years. And it would then go on to produce energy for maybe another 16 or maybe another 32 years. So ultimately, your return, your dollar return is much higher. But when you start to look at discounted cash flow and returns on investment, that longer payback period becomes economically challenging, and you've got to have an investor with the right sort of attitude. Very few people are prepared to invest in things that are going to give them their money back on 50 or 100 years' time for obvious reasons. But we do need to think about how these things would be financed. I think long term, economically very viable, but that long payback is a potential short term issue.
Yeah. Okay. Excellent. Well, probably got about 2 minutes left, and I just want to quickly ask you two questions if we jump back to oil and gas, just because I want to make sure we get these ones in. So
yeah, for sure.
Maybe just some quick answers before we run out of time. So the first one is drilling techniques in geothermal and oil and gas are quite similar. What are the differences in well construction between the two? If there are any?
Yeah, the key environmental difference is temperature. Not only does the equipment you're using to drill a well have to withstand higher temperatures, but also anything you put down there afterwards, any completion strings, if you do things like monitoring. If you're drilling a geothermal well and you want it to last to use it for a number of years, and particularly given the thermal conductivity issue I talked about earlier, monitoring the temperature of the well in the production zone is going to be important. So production equipment is going to have to be capable of operating for long periods of time at these temperatures as well. Because you're drilling basement rocks, you're likely to see a lot more shock and vibration while you're drilling as well. The other difference with oil and gas wells is that I don't want to make a sweeping across the board statement, but generally the reservoir sections, or what I call the reservoir sections, production sections, tend to be a little bit larger in diameter. Whereas in oil and gas, production might go down to about 6 inch, 6 1/8, 6 3/4 inch hole size. In geothermal, it's going to be typically between 8.5 and 12 1/4. And the reasons for that is that it allows you to get more flow through the well, and therefore take more heat away in the depending on the thermal capacity of the fluid that you're using.
All right, brilliant. Well, I think that's probably all we've got time for just now. So thank you everybody who did send in those questions. I'm sorry we couldn't get to everyone. There's a load of questions coming through here, John. So it's definitely a
I can
important and
see, yeah, thanks for all the questions. I don't know if there's anything we could do with all the questions that didn't get answered, because we could spend another couple of hours on them by the look of it.
definitely, yeah, there's a lot. So thank you for that. And thank you, John, also for a really interesting webinar and for giving us your thoughts on that. For everyone else, if you do, there's a couple of questions about these slides. These webinars are available on the IMechE webinar hub. They'll be there a few days' time, perhaps, and the old ones are there as well. So if you do want to go back through the slides or hear what John had to say all over again, please go through those and have a look, and join us on the 28th of February for the wind turbines. Thank you, everyone, and see you again soon.